Thank you for introducing me. Hi, I am Thanu Ganapathy. My presentation title is Acceleration of Coreless SoC Design Verification using PSS on Configurable Testbench in Multi-Link PCIe Subsystems. SoC design verification consumes the highest time span, approximately 60% of the SoC design flow. On-time release of SoC is vital for business. Speeding up of SoC design verification helps the on-time release. Objective of this presentation is to accelerate the SoC design verification using PSS on configurable test bench. Moving to next slide. Following topics are the contents of this presentation. First one is SoC design verification challenges. Here I'll cover SoC design verification challenges and in what are the challenges the proposed methodology helps. Second one is why PSS and why configurable test bench. Third topic is PSS overview. Fourth topic discusses about test bench customization and test generation with this methodology. Then I'll discuss about the results between previous and the new methodology. Then conclusion. Some of the jargons used in this presentation are PSS, that is Portable Test and Stimulus Standard. It's an Accelera standard. RP or RC, that is root port or root complex. They represent the host side of PCI Express. EP, its endpoint. It represents the device side of PCI Express. DSL, it stands for Domain Specific Language. It's a PSS language. Moving to next slide. SoC design verification challenges. There are many challenges in SoC verification. Some of them are mentioned in this slide. First one is quality of IP. If IP has bugs, the turnaround time of IP bug fixes can be more and it can affect SoC verification timeline. Next one is simulation runtime. Some of the SoC scenarios run for multiple days. Issues in long-running scenarios can drag SoC verification. The next item is tools and methodologies. Less optimized tools and methodologies can also affect the SoC verification timeline. The next challenge is verification test vector coverage. The challenge here is finding and covering all the essential test vectors and running them. We have to cover all the corner case scenarios which are critical. The next challenge is glue logic and integration issues. SoCs most of the time come up with glue logics. It may require some new test plan also sometimes. Integration issues are very common in SoCs. Earlier we find and fix them, faster the SoC verification can be. The next challenge is concurrency and scheduling. It mainly deals with multiple IPs running in parallel. The last challenge is features per timeline. Usually features get added from project to project, but timeline of SoC verification remains the same. Hence, we need efficient techniques to verify all the features within the same timeline. Some of these challenges can be handled better with our proposed methodology, that is PSS over configurable test bench. Moving to next slide. Why PSS? Before why, what is PSS is the one I would like to talk about. PSS, as said before, it is portable test and stimulus standard. It's an accelera standard. It helps with portability of stimulus across platforms or across verticals. With PSS, we can use the same stimulus at IP verification or at subsystem verification or at SoC verification. Similarly, same stimulus can be used across platforms like virtual platform, FPGA, or emulation, or post-silicon validation. That's the broader scope of PSS. But in this proposed methodology context, the following features are leveraged. First one, PSS helps with quick generation of many legal scenarios for a given base scenario. It does the autofilling of unselected parameters, that too only legal or the right parameters. It provides self-checking, that is, if any parameter is inconsistent to the provided spec information, it will throw error and a scenario will not be generated. Fourth one, it helps with virtual sequencing and scheduling. Moving to next slide, why configurable test bench? In our test bench environment, before the configurable test bench, elaboration snapshot was unique per link, or here link means controller. So for each PCI link, it was unique. Hence, it occupied more space and time. But with configurable test bench, we have single elaboration snapshot for multiple links. While running the test from the command line itself, we can control the selection of link and the configuration of the link in the configurable test bench. We can also run multiple links concurrently with configurable test bench. The second item, that is, in the old test bench structure, the addition or removal of a link was a cumbersome work. The common tasks and functions had difficulty in editing. But in the new test bench structure, it is easy to add or remove a link. Moving to next slide, it is PSS nuts and bolts. PSS tool is a vendor tool that we used. We provide inputs to the PSS tool and we get outputs from it. The C scenario output that you can see on the right hand side is the test case that we generate out of it. Inputs required are discussed first. The first one is system configuration information. A spreadsheet with DDR address information, processor or driver information are provided in this. Next is PCI configuration information. In this also a spreadsheet with all the PCI controller related information, supported speed, mode of operation, link width, etc. are also provided as input. Next is TB task implementation. To be compatible with PSS calls, the test bench tasks and sequences have to be customized and parameterized. Next one is platform binding. We use SV-UVM test bench and hence SV platform binding information has to be provided. I remind that PSS supports multiple platforms and hence we have to provide the platform binding information. Next one is base model. Base model captures the basic building block of system and functionality in PSS actions. I will give an example of action in the next slide. I would like to talk about the PSS tool a little. PSS tool has PSS libraries, DPI. DPI is for CSV interfacing the calls within those, between those. It has scheduler. It has provision for modeling scenarios. It has implementation mapper. That is the SP code that lets the communication between generated C scenario and the existing SV-UVM test bench. That is the implementation mapper. It is an SV code. PSS has autocompleter, solver, and self-checker. They were all already explained. The output of PSS tool are C scenario. It is basically the generated test case. Gen time coverage. That is, we get the coverage information at the time of generating scenario itself. The next one is C SV-UVM integration files. Here we get PSS collaterals, which helps in execution of C scenario in the SV-UVM test bench. Moving to next slide, PSS base scenario sample code. Using DSL language, a base scenario is coded. Default values are provided as parameters for the base scenario. The scenario shown here has two PCIe links. That is link 0 and link 1. That can run concurrently. You can see parallel there as syntax. That is the one which indicates that they can run concurrently. You can see that RC memread and EP memread and all, they are the actions that are supposed to be created and which are leveraged by the scenarios. This is what I mentioned as action when I was talking about the input to the PSS tool. Moving to the next slide, PSS generated scenario. The loaded base scenario is configured with different parameters. That is, you can see that the parameters are configured in the tool and it is varied here from the previous slide. That is, the lane number is 1 here and link speed is Gen 3 here in the generated one. But you can see that the previous slide has lane number is 2 and link speed is Gen 4 for the link 1. So that is being changed here. So this is the one that is done in the PSS tool, and hence the variation is. I would like to tell that this particular slide is only for illustration purpose, as the generated scenario is actually a C code, and this illustration is to indicate that the parameters, what kind of parameters that we change in the PSS tool. Moving to the next slide, Testbench customization. Here, how PSS is integrated to UVM Testbench will be discussed. The top rectangular box is the Testbench top module. PSS SV top is instantiated here. The PSS SV top has initial block. Hence, once the simulation starts, the PSS also starts. The PSS main task has a fork join. As you can see, there are 3 threads. The PCIe VIP 1 main, PCIe VIP 2 main, and the AXI VIP main threads are there. I would like to inform that we are using Coreless SoC, hence the AXI VIP is used. Here I would like to take the example of PCIe VIP 1 main. Here you can see that the PCIe VIP 1 main is called from PSS SV top, and the implementation is in the generated C code, as you can see on the right hand side. In the generated C code, you can find UVM wait for scenario main. It loops and waits for a call from the UVM test run phase. That is, the run phase from the UVM test will unblock it. As you can see, the run phase in the UVM test, after the boot sequence got executed, there is a scenario main called, and which is unblocking the C's UVM wait for scenario main, and then the generated scenario gets executed. The next slide, Testbench customization. Here, C, that is the generated C test, get how it gets executed in the UVM test bench. That we'll see that. As an example, outbound write is considered. You can find arguments in the task call. These arguments are coming from the PSS tool where we configure it. It calls the task in the PSS SV top, as you can see. So the generated C code outbound write is calling the task from the PSS SV top code. This SV top code is nothing but an implementation mapper which connects to the existing SV-UVM testbench code. That is, it is calling the task from the existing SV-UVM testbench, and the arguments are passed to the existing SV-UVM testbench. You have to note that we have to customize our existing SV-UVM testbench in order to receive these parameters. Moving to the next slide, test execution flow. The first step is create the base model scenarios, then load them to the PSS tool. Here we have to compose and solve the scenarios, and then generate the test with adapter. Adapter is the one which supports the execution of C scenario in the UVM test bench, and then run the generated scenario in the UVM test bench with the simulator. Here we use event simulator, and then we can debug and analyze the runs. Moving to the next slide, testbench customization. Here the pictorial view of configurable testbench structure will be discussed. We use common sequence libraries for multiple PCIe controllers. We use virtual sequencer. The virtual sequencer uses dynamic array for the number of PCIe links. We use common tests for all the links. Moving to the next slide. Summary of PSS configurable testbench flow will be discussed here. I will talk about steps in the PSS flow first. First one is develop PSS collaterals, then develop spreadsheet each for system configuration information and PCI configuration information, then develop implementation mappers, then develop base scenario models for the PSS, then load the base models and generate the scenarios that are required. With respect to UVM testbench flow, customize and parameterize the existing tasks and sequences first, then add necessary leaf level tasks to accommodate the calls from PSS, then develop the parameter files and support files for the configurable testbench, integrate the PSS top to the testbench top, and call the scenario main from the run phase of each test after the boot sequence. Include the generated C code in the test execution. Moving to next slide, result comparison from effort perspective. You can see the one in blue is the initial effort. The old testbench structure required less initial effort, while the new testbench structure required more initial effort. The one in orange, that is the generation of scenarios. The new test bench needed very less effort with respect to generation of scenarios, but the old one required more. The one in gray, that is the test case debugging effort. The one in the old test bench structure required more debugging. It's a very huge effort compared to the new test bench structure. The initial effort is a one-time effort, and that is attributed towards parameters of UVM sequences, creation of SV task wrappers, all those things that were discussed prior. This is only a one-time effort, and subsequent projects does not require this initial effort. If you see this, overall 75 days was consumed by the old testbench structure, while the new testbench structure consumed only 50 days, despite being the first project. Result comparison is continued with respect to runtime now. That is the wall clock time. You can see that 320 runtime days was required by the old testbench structure, while 180 runtime days was required by the new testbench structure for the same set of scenarios. With respect to disk space consumption, old testbench structure required 6.4 terabyte, while the newer one required just 3.5 terabytes. Conclusion. As discussed before, the first time development required good amount of effort with respect to new test bench, but the subsequent project can reap the benefits manyfold. Here you have more legal scenarios in less time. Here the benefit of less test case issue debug will be there. Here we can cover more corner case scenarios in the new test bench. So the SoC design verification gets accelerated due to this. We recommend this methodology to the design verification engineers. With this, I conclude my presentation. Thank you.